Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question raw and uncut. So we have a medium today. It's called maximize the number of target nodes after connecting trees 1. So we're given an edges list. We're actually given 2 edges list and a number k, and we want to return a list of ints. So let's see like what are the size. So yeah, I think like there are 2 trees, right? So for both trees, it will be at like it will have 1,000 nodes at most. So like it will have n-1 and n-1 edges because it is a tree. Yeah, okay, so it just describes a tree basically, like for both of them. And it is guaranteed that it is a valid tree. And also we have a number k, which is it could be from 0 to 1,000. So let's read the question. So I think that's kind of what we said. And also it seems like it is bidirectional. So yeah, so node U is target to node V if the number of edges on the path from U to V is less than or equal to K. Note that a node is always the target to itself. So the number of edges on the path from U to V, so how far away it is less than or equal to K. So like for example, if K is 2, then U and V could be like 2 apart, I think. So return an array of n integers answer, where answer I is the maximum possible number of nodes target to node I of the first tree if you have to connect one node from the first tree to another node in the second tree. Okay, I think like for this question we do have to look at the example to like completely understand what is going on. Also, note that queries are independent from each other. So for each query, you remove the added edge before proceeding the next query. Right, so you have to like add an edge. Wait, return array. So answer I is the maximum possible number of nodes target to node I of the first tree. Right, so we're going like from the first tree. If you have to connect one node from the first tree to another node in the second tree, so we want to like get the maximum amount of targets. I'm actually not too sure what's going on. So for example 1, we have 2 trees and then k is equal to 2, right? So I think yeah, that's tree 1, and then what was tree 2 though? So 0, 1, 0, 2, 0, 3. Right, so that tree is 0, 2, is tree 2, and that is tree 1. So for I is equal to 0, we can connect node 0 from the first tree. So it is suggesting we can connect these 2. And then we will have 1, 2, 3, 4, 5, 6, 7, 8. And including itself, it will be 9 nodes that are 2 apart. And then for I is equal to 1, again, it is suggesting that we can just connect these 2. But for 2, 3, and 4, it is actually saying connecting to node 4 is better. So for node 2, node 2 it will be touching like all the stuff from tree 1 already. So it'll be like 1, 2, 3, 4, 5, and then if it connects to this, it will be 6. Wait, 7, 8, 9 though. Why is it only 8 there? Yeah, I'm a bit confused on what the question is actually asking now. Let's try to read this again. This is like kind of wordy. So if the number of edges on the path from U to V is less than or equal to K, right? So yeah, my understanding is correct. So if you start at node 2, you like, and if k is 2, you just basically BFS like to depth 2 outside. Um, so return array maximum possible number of nodes is it? Yeah, the number of nodes target to node I of the first tree. If you have to connect one node from the first tree to another node in the second tree. So yeah, I think what I thought about is correct, right? So like if one connects to 0, well, so who are one's targets? It will be 102, so that's 3. And then it can connect to 0, which is 4. And then it can go to like 2, 3, and 1, so 5, 6, 7. But yeah, I don't understand why 2 would only be. Oh wait, 2 is actually 9. I think I'm just tripping, right? Yeah, okay. So 2, if we connect it to 4, it will be 1, 2, 3, 4, 5. Yeah, okay, 6, 7, 8, 9. Yeah, okay. Um okay, I think I understand the question now. So basically, like, you have to find the optimal place to link your node so that the maximum amount of node becomes a target. So I think like my first thought is, if we are connecting to tree 2, why isn't why can't we always only connect to the best node? Because so let's say you have a first tree like here. Yeah, something like this, right? And like k is equal to like I don't know, 3 or something. Well, whatever node you connect to on the second tree, so whatever this second tree is, right? Maybe something like this. Well, whatever you connect to, like on the second tree, it actually like it'll be depth 2, right? Like, because like you have spent one move to like connect to it, so you just want to find. I think like what you want to do is you just want to find the node on tree 2 that has the most connection with depth 2. And yeah, actually, like looking back at this case, so we have k is equal to 2, right? So we want to find the node that has the greatest depth for depth 1, in which actually like the reason it picked like node 4 and node 0 is because both node 0 and 4 has the same amount of depth 1 nodes. So like each of them, they have like 3, right? So yeah, actually this is only to like throw you off. But yeah, so the only thing you have to do is well, because we only have 1,000 nodes, it makes sense that we can do a BFS on each node on tree 1, and also we can do a BFS for each node on tree 2 to find the node with the maximum amount of targets for a depth of k minus 1. So yeah, I think we can just code it out now. So of course we need our adjacent list. We always do when we deal with these questions. So adjacent list 1, adjacent list 2. How do we find out how many nodes we have? Yeah, it doesn't tell you how many nodes are there, which is quite annoying if you ask me. So there are 2 ways of doing this. Either we find the maximum. Yeah, I think let's just find the maximum like that. So we have n1 and then we have n2. Or we can just use a map, honestly. So a default dict, because it doesn't tell you default dict list. So we need to import that. Import default dict. So for something. Oh yeah, but then now we have to like. Now we have to like gradually allocate. Actually, we don't. We can just do this. So basically, what this will store is it will store the node, and then it will have a list of children, and like we can like gradually add them into the default dict, because we are not bothered to find how many nodes are in tree 1 and tree 2. Okay. So for AB in edges 1, we can just do adjacent list 1, A, append B. And because it is a default dict, it will just automatically do that. So yeah, so like it will automatically create the list for you instead of like a normal map. Yeah, okay, so now we have the adjacent list for both trees. The first thing we want to do is find the best node on tree to connect to. So basically what we want to do is I think we just want to go from each node that has a connection. Yeah, we just want to. So like for our adjacent list, like basically all the nodes that are present in tree 2 would be one of the keys, right? So we can just loop through all the keys. So for node in adjacent list 2.keys, yeah, we can just do that, and then we can do a BFS. So we have a scene set, and then we should also have a. I think we can use like the 2 queues kind of method to like to deal with the BFS. So we have like Q is equal to that. Well, actually we have to start with node. Like that will be the current node we have, right? So and then we have like depth is equal to so we actually want to BFS out twice, right? Like if k is 2, we want to DFS out like k minus 1 times. So we start at 0, and now while q and depth is smaller than k, k minus 1. So we want to DFS out. So we have a new queue, and then like we want to get all the nodes there, right? So now so while like there's still nodes in queue, so we want to get the node. Yeah, let's just call it like let's call this root then. So that will be the starting point basically. So node, and then we have so we can just do q.pop, like to basically get our elements in our in our stack. It's just a way to like store the previous the nodes in the previous depth. So if we have seen that node already, we don't want to look at it again, so we'll just skip that. And then we need to add our new node into scene. And so now for children, so for the child of that node, in adjacent list 2, node, we want to add that child. Yeah, I think maybe if we check whether we have seen the child first, it will be more efficient. So if child not in scene, so we haven't seen that yet, append child. So we'll just add that on, and so we'll go through like all the we'll go through all the queues, like all the elements in the queue, and then we'll set like queue equals new queue, and also we'll append our depth. So at the end, yeah, so at the end, we should have a bunch of nodes that we have seen, and we could also have some nodes that are still in our queue, but because like we have reached our maximum depth, we haven't actually like used them and put them like into the scene node. So actually, our sum is so like the number of nodes that are of target, like that are targets of the roots, would be it will be a length of scene, so whatever is in scene, and also like plus the length of queue, so that would be like the nodes in the last depth. So imagine like if we start at 0 and we only want to reach out to like depth 1, right? So we have like 1, 2, and 3 in queue after we did that, like did this step here. So yeah, we have to oh yeah, actually, yeah, so k could be 0 as well. So actually, what happens in that case? I think like we might have to deal with the edge case as well, because like if k is 0, this would be like -1, but we can't actually reach the second tree. So yeah, let's put a note up here. Deal with k equals 0 edge case. But yeah, basically this is gonna get us the well, this is gonna get us the best. Well, it's gonna give us the number of targets from root with like k-1 depth, and we want the running best, right? So so that means like we have to store yeah, I guess like the max target on tree 2. So we start at -1, and then like here we'll just do max target. Yeah, I'll just call max target. Is equal to either the running max target or our current root. So that should give us the like that should give us what we have for tree 2. So what that means is we can just connect. Yeah, we can now look at each of the node in tree 1. So let's have a look. So I think like for each root in node 1, so for I think like what we want to do is we can just get the maximum of the keys, and that should give us the number of nodes there. Yeah, I think that'll work. Or we can just do like for root in adjacent list 1 dot keys, and then like we can do sorted. I think that should work as well. So this is just a dumb way to like go from 0 to 4, for example. There are definitely better ways, but I'll just go with that because it's not detrimental. Yeah, and then of course we want to run our BFS again to actually get how many oops ah no. No, yeah, I'm just gonna copy. I'm gonna use my mouse. Um, yeah. Okay. So, just gonna copy the algorithm above. But like, instead of reaching like only to k minus one depth, for like inside tree one, we can actually go up to like depth k. So like we'll do the same thing. Yeah, except we have to change this to adjacent list one, and we basically do the same thing here. And also instead of doing this, we'll have our result, which is going to be a list of ints, right? So because like we are doing like from zero, like we were doing it in order, we can just keep appending the answer, right? So on tree two, we can connect a max target amount of nodes at most. And then like we can just add whatever we have seen, like whatever we can reach on tree one. So that should give us the answer. And at the end we can just return res. I'm not sure. Okay, it does seem like it works. But let's see. Oh, well, that's not good. So in this case, yeah, well, I wrote I have to deal with the zero case, but I forgot to deal with it. So actually, for the zeroth case, each node is only the target of itself. So we can just return. I think like we still have to get the number of the number of nodes. Oh, oops. Yeah, so we still have to get the number of nodes. Like inside adjacent list one. So I guess we can just reuse this honestly. And what we can do is we can just go here and do like if k is equal to 0, max target should become 0 because we can't actually reach tree 2. And so if this is 0, yeah, I'm pretty sure it should work now. Like the only issue is like we have 1 as our max target when we have k equals 0. Yeah, and that was the issue. I literally wrote down the edge case that I have to deal with, but I didn't deal with that. Yeah, okay. So I guess I can talk about how I solved the problem. So like again, when you're solving a LeetCode question, the first thing you usually have to notice is the bounds. So like, what are the maximum number of elements you can have, right? For example, so if this is like if this is 10, if this is 100,000, it would be a different story because my algorithm right now actually checks actually BFSs from each node out to like all the all the other 1,000 nodes, right? So if this is 100,000, it will be definitely too slow, and we will need like some smart ways to like actually like to basically like for example like for 0, like if we can reach like I don't know like n targets, when we move to 1, how many do we actually lose, and how many do we keep and stuff. So like it'll be a whole different story if we have a lot more nodes. But well, the first thing I noticed is it's only up to 1,000, so we can have an n squared solution, or even like n squared log n. Right. And then the second thing I noticed was that because each of the connections are independent, we actually only have to like, and we want the maximum, right? So we only actually have to connect to one node, because like that one node would keep giving us the maximum, right? So it doesn't matter like which node from tree 1 you're connecting to tree 2. We can always just connect to the node with the like maximum amount of targets with like the k-1 depth. And it is k-1 because like from tree 1 we have depth k, right? If we use one edge to connect to tree 2, it will be k-1 depth. And yeah, so we just need to like find the maximum here. And how do you find it? Well, like whenever you have like these tree or like these kind of problems, I think that whenever you have trees, you should either think about recursion or BFS and DFS. So well, obviously BFS works here, so I use BFS, and like to find the targets within tree 1 as well, we can again like use BFS. So that's kind of how I thought of the solution. It is quite long, like, and quite wordy for this solution. But I guess I guess it's fine. Like it's a bit annoying to code up, but yeah, I don't think this question is too hard. So yeah, if you have any questions, make sure to comment below. I'll try to answer them. And thanks for watching. I'll see you tomorrow. Bye.